Okay, I'm going to go ahead and get us started with today's seminar so that we make sure we have ample time for conversation after the talk. Welcome everyone to today's Spatial Analytics and Data Talk with Martin Fleischmann, who'll be talking to us about spatial signatures, dynamic classification of the built environment. Martin is a research associate in the Geographic Data Science Lab at the Department of Geography and Planning at the University of Liverpool, and a member of the Urban Design Studies Unit at the University of Strathclyde in Glasgow. He holds a PhD in architecture from the University of Strathclyde, where he focused on urban morphology and quantitative aspects of the characterization of urban form. Martin's research interests lie in urban morphology and geographic data science, focusing on quantitative analysis and classification of urban form, remote sensing, and AI, bringing together the architectural aspects of the description of cities with geography and data science. So just a couple of housekeeping matters, and then I'll turn the floor over to Martin. We will use the questions in the Q&A after the talk to get discussion going. So while Martin is talking, you can feel free to drop those. You'll see a little button at the bottom of your screen in the Q&A. That's much better. You can upvote questions. Works a lot better than the chat. And you can tweet Martin's talk using the SAD 2020. I'm still using SAD 2020 because it's a very long year for me, or SAD 2021. And then people will be able to see the conversation in real time. And with that, I'll turn the floor over to you, Martin.
Thank you, Rachel. It's a real pleasure to be here with you today. Just gonna start sharing the screen. Hopefully everything works right now. Thank you for the introduction. It was really nice, so I don't have to introduce myself again. Today I'm gonna talk about cities and about the way how we can look into their structure, and mostly about the project we work on with Danny Aribas-Bell in the Geographic Data Science Lab at the University of Liverpool, which is called Urban Grammar. And what you will see today is a part of the first stage of the project, let's say. And with that, let's go to the presentation. How do we arrange stuff in cities matters. The cities over the years have shaped in very different ways. And the way they are shaped now shapes us. And it matters a lot. There's a lot of research in academia about the effects of the way how cities look like to different aspects of life. But there's also a lot of focus on form and on cities and their appearance in policy. For example, the latest British report, Living with Beauty, which aims to deliver beautiful places again in the UK, work with sort of retrofitting urban sprawl into more walkable, livable places, or the work which happens on the Global South, where a lot of effort looks into the informal settlements and other neighborhoods of similar type and their form, and how that form affects the life of people and how that form can be worked with. And I will talk a lot about urban form today. And when we talk about urban form, we can ask a question: what does it look like? What the city looks like? So we can sort of define it as a physical structure and appearance of cities. And when we talk about urban form, we can ask what exactly that means. What is urban form? And there is a field of studies focusing on urban form, which is called urban morphology. So we can ask, what do we talk about when we talk about urban morphology, about the study of urban form? Urban morphology is a sort of hybrid field, which was first established around in the 1960s, at the same time in architecture and in geography. And at the moment, it sort of covers this range between geography, which can be seen as a top-down approach of understanding the structure of cities, and the architectural one, which can be seen as a bottom-up, so from buildings and their transformation up to neighborhoods and cities. And this field sort of agrees both of its legs, that there are some fundamental elements of urban form and which we use when we talk about it and we analyze it. And those are buildings. Everyone sort of can imagine what the building is, even though the definition sometimes is a bit tricky. Streets, and that very often is conceptualized as street networks. So we have just a abstract, let's say, graph representation of our street networks with segments between intersections and so on. But it can also be the street sections, street segments, street space, and streetscape. And the third, or the fundamental, so-called fundamental elements of urban form is plot, and that's the most complicated one of them because it's tricky conceptually, and it's tricky to get data on plots, and it's tricky to get data which conceptually mean what we mean by plot in urban morphology. And then sometimes we also include open spaces. We include study of parks, squares, and other places which are not necessarily buildings, streets. And we ask a question how to describe it. And because we are data scientists, we ask a question how to describe it numerically. And there is a subfield of urban morphology growing in recent years, which is called urban morphometrics. And it can be defined as a quantitative analysis of urban form. So it's all about measuring. We are looking at these elements of urban form and their aggregations and combinations. We are trying to numerically describe what those features are, how they look like, how they are organized together. So we are measuring, and there is a wide range of things we can measure. There are some which are more common than others, but we can generally organize them into roughly 6 groups. We can measure dimensions. So take, for example, a building, and you can measure its area, its height. With street, you can measure the distance between intersections, or can measure the length of streets within a city. We can measure shapes. We can measure whether the building footprint is more similar to circle or square, or whether it looks more like a fractal shape, how complicated it is. Or we can look into a street segment, whether it's linear, it's a direct line from A to B, or whether it's really curvy. We can measure spatial distribution that mostly entails relationship between different elements. So we can try to understand whether 2 buildings touch each other, how many buildings which are touching are within the same sort of component, whether buildings which are next to each other have the same solar orientation, whether the orientation of street is perpendicular to the orientation of building, or whether there is no relation whatsoever. We can also measure intensities, and that's one of the most common because all the measurements of density belong to it. So we can look into covered area ratio, floor area ratio, but we can also measure the granularity of a street segment as per how many buildings are along that street. We can measure connectivity, which mostly focuses on street networks. So how well connected it is, what are the main thoroughfares, and other aspects. And we can measure diversity, which means how diverse all these things are within a certain area. Are all the buildings same, or is there a high variation? We have small buildings next to large, tall buildings next to a short one, or whether they are all the same. And why are we doing all this? As I mentioned in the beginning, there is a large body of literature looking into effects of the way how our cities look like and other aspects, from economy to well-being, and essentially anything you can think of. You will find a paper on that. But very often, the conceptualization and quantification of form in those cases is sort of simplistic. Very often we see that the form is classified only based on density. I would say that's not enough, because we can have 7, 8, 9 places with exactly the same density, but with very different urban patterns. So we are trying to measure wide spectrum of these morphometric characters to capture the form as close as it is and as complex as it is. And also because we finally can do this, because in recent years, we've been able to work with proper data we need. It can be OpenStreetMap, which gives us street networks with close to 100% coverage all around the world, gives us 60% of coverage in case of building footprints. Or it can be a spectrum of open data portals, either municipal ones or the national ones, where we can get the data of various kinds, or the data of remote sensing origin, like the famous Microsoft Building Footprint dataset, which covers several countries in North America and Africa at the moment. You can get those data and they reflect the morphology, and you can work with it in morphometric models. And we also have tools which we didn't have a while ago. We have OSMNX by Jeff Boeing, and if you attended Jeff's talk, which was part of this seminar series back, I think in January or February, you know what I'm talking about. And if you didn't, I recommend checking it on YouTube. But OSMNX essentially takes care of fetching the data from OSM, cleaning them, and Jeff is using it for analysis of street networks quite a lot. We have Spatial, which is Python spatial analytics library, which gives us a lot of core components, so we can build on top of it our photo analysis. So the spatial wise matrices, which helps us understand which features are next to each other, and other advanced spatial enabled algorithms are all within Spatial library. There's a brand new addition, which is called Food, which is from our world. It's written by Chris Jochem from World Pop Group at Southampton University, and that focuses on description of urban form on the basis of a grid. And there's a MOMPI, which is a tool we are using, and which is used throughout this presentation. And I will talk about it briefly to introduce what it is. Development of MOMPI started back at the University of Strathclyde a few years ago, when we wanted to get a classification of urban form, and we wanted to use morphometrics, but we didn't have any tools how to do that. So we decided to develop this measuring toolkit, which is essentially open source Python software, which can guide you through the morphometric analysis from the pre-processing of data a bit, through the generation of some additional morphometric elements if you need them, to measuring all those 6 categories I was talking about. And it's aimed to be an open repository, so we are trying to get in touch with other researchers working predominantly with Python and link their research into MOMPI, so it can work as a big repository. And if you need to describe urban form in some way, you could be able to go to MOMPI, find your tool, and use it directly on your data. I will show a few examples how MOMPI can be used and how morphometrics can be used before we maybe move on to spatial signatures and to the classification of urban form. So I haven't shown any images so far, so a few maps in here, one per category. In here you can see a small town of Kala in Germany. And what you can see on the map is the longest axis length of a building footprint, which can be seen in some way as a proxy of how big of a barrier that feature is in a space. We can also look into the equivalent rectangular index of building footprints, essentially telling us how similar the building footprint is to a rectangle, how complex that shape is. You can see that those most simple buildings are shining compared to some of the more complicated. We can talk about distance to neighbors within a spatial distribution group. And here you can see that the historical core where the buildings tend to be more closer together, the urban form tends to be a bit more granular and compact. It's highlighted on this map. And you can also talk about covered area ratio. And in this case, we didn't have any spatial unit. We had only building footprint. So we had generated something we call morphological tessellation, which in principle is Voronoi tessellation based on building polygons. I will slightly talk about it later, but I won't go into much detail. Regarding connectivity, you can see that we have closeness centrality, which measures sort of compactness and connectivity of street network, how permeable that is. And that is measured on intersections, because when you turn your street network into a graph, you can work with both intersections as units or your edges as units. This one is measured on intersections. And the final one can be Simpson diversity of tessellation area. So we specify context around each building, and we ask, are those generated tessellation cells all the same within the area or not, compared to the rest of the data set? The second example we used very recently was to look into the evolution of urban patterns. There is a range of research looking into evolution of street network patterns, done either at Strathclyde, I think like 6 years ago, or there are two papers recently published, one by Jeff Boeing and one of which I don't remember the name, and I'm really sorry for that. And we had the question, is the change they observed similar in other aspects which are not related necessarily to street network? So we selected 42 places, divided them into 6 historical periods, and we got a data from OpenStreetMap within a 400 meters buffer around the center of our case study area. So you can see the different categories we have used, from pre-industrial, historical, either medieval or Renaissance Baroque developments, through industrial areas which are typical with the gridiness, to garden cities, modernism, neo-traditional, which is sort of switch back to Garden City, like Garden City version 2. And we also included the informal settlements. And we measured a range of morphometric characters, and we looked how they change. And I just give you a peek of that. And if you want to look into the scale, I'm showing here 3 different morphometric characters. We look into the distance between buildings, which is the top one. We can look into the area of tessellation cells, which is the bottom left, and we can look into the area of building themselves, which is bottom right. And you can see that there is a gradual change of scale towards modernism, where the scale peaks, where we build everything larger, further away from itself, bigger. Everything was huge. And then it's slowly getting back. We don't have the very recent developments, because it's hard to get the area of 400 meters buffer, which is fully built, let's say, after 2000. But one thing which I'd like to point out here is that a lot of neo-traditional developments claimed that they want to build urban form which is similar to what was in the industrial area, like classic tenement houses, perimeter blocks, and things like that. These as well as results by other researchers show that it's very often not the case in reality. So even though the places may visually look like the historical one, they structurally are more closer to either garden city or in some cases even to modernist areas. So we have to try to understand the deep structural components of urban form before we try to design something new which imitates something which was there before. Oops. And this is also an interesting one. We forgot how to make a grid. The top figure here shows a meshedness of a street network, which is a proxy of a griddiness kind of. And we can see that the only period which tends to predominantly be griddy is industrial, which is seen also on the bottom left, which is the linearity of street segment, which measures whether the street segment from intersection to intersection is a straight line or whether it's a bit curved. We kind of forgot how to make a grid after we started building garden cities. But it's just a sneak peek, because the core thing I would like to talk about today is classification. And specific type of classification we call spatial signatures. Spatial signatures are characterization of space based on form and function. You can see that I was talking about form only so far, and in this point we are also including function into the formula. Designed to understand urban environments, which is the main focus. But as you will see, the spatial signature not only environment, so we cover the entirety of space. So we have two main components: form, which I sort of covered already. What does it look like? What is the physical structure and appearance of cities? Which can be described qualitatively. Let's say we want to look into the transformation of place, and we look how different buildings change and the cycle which is behind that, which is typical aspect of traditional urban morphology. We can have some quantitative case studies focusing on densities and other aspects. And we can do morphometric study, which tries to include more than that. And we can also work with remote sensing when we describe form. While function answers the question, what is it used for? So not only how it looks like, but what the place is used for. So those are the activities that take place within an environment. And that's the domain of geography, economics, sociology, environmental sciences, transport studies, and many other fields. And why are we combining these two? Because they don't really match always. They're not very often used together. Why are we combining them? The combination of form and function in the single classification gives us a richer picture. So we're not following only one aspect. We're trying to get closer to reflecting the complexity of place. Because we can work with topography, we can understand different historical layers of the place. We can understand different cultural values and different cultural aspects which shaped and shape each of the places. And by combining it, we get more robust representation of built environment than if we used only function or only form. At the moment, when we look into the literature, we don't really have good ways of measuring both form and function in cities at the same time. We have research which is either detailed, scalable, or consistent, or two of these. Very rarely you will find the research which is at the same time scalable, at the same time consistent and detailed. Typical example of research which is detailed and consistent is a qualitative study of urban form or qualitative study of place. We have consistent methodology, we have detail we need, but it's hardly scalable to, let's say, national extents. We can talk about research which is scalable and consistent, like a gridded population estimates, which can go to global extents, but they often like the detail, the smallest component. We can talk about research which is detailed and scalable, but that often depends on very specific set of input data. So for example, even geodemographic classification of output areas of British census would be different for England and for Scotland because they treat their data differently. So we're trying to find a way how to make a classification method which is at the same time detailed, scalable, and consistent. Because so far, if we are looking into different aspects of built environment, it gives us a bit of fragmented understanding. At the one side, we know what the geodemographic profile of these places is. On the other side, we know what the physical classification is, what is the land cover or land use, or what are the patterns of its urban form. But we sort of struggle to make a link, make a bridge between these two. And that's where we are trying to plug spatial signatures. And if I shortly will give you an overview on how the method works, I can talk about 3 steps. And now I would like to point out one thing. Method for classification of spatial signatures is not necessarily a strict methodology. It's more a way of thinking about built environment. Because as you will see, it doesn't really require one standard of input data and one set of input data. It really depends on what is available kind of and what we can work with. These 3 steps of spatial signatures can be seen as making building blocks, filling building blocks with data, and generating the signatures. The first step is generation of the basic spatial unit we use throughout the work, which we call enclosed tessellation. You may recall that I was talking about morphological tessellation before, and enclosed tessellation is slightly different, but they have a lot of commonalities. Enclosed tessellation is derived as a 2-step procedure where we first have a set of barriers limiting space like street network or rivers, coastline, or railways. And we divide the space based on these barriers. So on this diagram, you can imagine that those blue lines are the barriers. And then we generate morphological tessellation within each of these so-called enclosures. So this is how it would look like in Barcelona, for example. The blue are the streets, center lines, which we used as a delimiter in this case. And then we use building footprints to further subdivide these enclosures. And this spatial unit covers the entirety of space. So it can cover also unbuilt areas because they are still delimited by certain set of barriers. And they adaptively change their scale based on the content, which means that if we have granular city center like this one in Barcelona, we have enclosed tessellation cells which are small and granular and closely packed together. Well, if we go further away to the countryside, we can have enclosed tessellation cells which have kilometers across in some cases. And this allows us to adapt to the changing nature of the environment. And with these spatial units, we go into the classification of form, well, description in this case, description of form and description of function. And we try to link every piece of information to each individual enclosed tessellation cell. So we measure so-called characters of form based on buildings, based on enclosed tessellation cells, based on street segments or street nodes and their connectivity, based on their context, based on different aggregations, and based on enclosures. And we also measure function, which can cover population estimates, which can cover workplace population estimates, land use, and then cover accesses to different uses, densities of activities, or the greenery. We are using often NDVI index to estimate how green each tessellation cell is. And every piece of information is considered within its spatial context, not by itself, but within the wider area. And we have few ways how we are doing this depending on the nature of each character. But sort of one of the most common is application of the notion of contiguity on tessellation. So we around each tessellation cell, we define an area of 10 topological steps, and then we consider each of the cells within this area weighted by the inverse distance between the cell and the target cell. So we have definition of a context, which again adapts based on the structure of place, but still what is closer has higher value than what is further away. And with this, we generate spatial signatures. So you can imagine that for each tessellation cell, we have a few hundreds of characters as a combination of those capturing form and those capturing function. And because we are doing that within a specific spatial context, we are also trying to understand what is the distribution within that context. So very often we look into the first, second, and third quartile of the distribution. That's why we have such a large number of characters. And spatial signatures are a result of clustering algorithm and sort of dissolution combination of enclosed tessellation polygons into contiguous areas. What are the benefits of this approach? It's data-driven. Even though we have to make a lot of decisions along the way about how to link different data, how to link population to tessellation, or how to work with accessibility-based measures. It is still data-driven, and it is theory-informed. The whole methodology is granular because you can see that it can go into the detail of individual buildings, and it's scalable. It's a whole written in Python, and we are trying to make the whole procedure as performant and scalable as possible using parallelization, Dask backends, whatever that is. But we're trying to enable the analysis for large areas, go to national and even larger scales. And it has a flexible deployment. Everything is open. Everything is sort of enclosed in Docker containers, so we can get our environment, deploy it on a large server, make a large analysis on place we never seen before, and then use it within the analysis of the, let's say several places. To give you some illustration of what I'm talking about, I haven't shown any images again. We used 5 different cities from around the world, based on different historical environments, based on different geography and different culture, and importantly, using different data landscapes. So we will look into Barcelona, historical city in Europe with amazing open data portal, describing every single aspect of the city. We will talk about Houston, one of the example of North American cities, typical with sprawl, large metropolitan area. We didn't have building footprints from the original data source, but we used Microsoft Building Footprints dataset, which is derived from remote sensing. We will look into Medellin, South American city, which had some open data from their local open portal, but it's a city which has a very different history and very complex topographical situation. We will talk about Dar es Salaam in Tanzania, where we used amazing data from OpenStreetMap, which were generated as part of the humanitarian mapping project a couple of years ago, and as such are reliable and cover large area of Dar es Salaam. And we'll talk about Singapore, a city which its growth is restricted by the boundaries of the island. As I said, we are using different data. We are using open data, OpenStreetMap, satellite derived. We are using data for function coming from global grids, let's say population estimates, or global land cover, or global night lights, which can be used as a proxy of land use, and especially they can pick the large industrial areas. And each of these places used a slightly different set of data to illustrate that spatial signatures is a way of thinking about the environment, not a strict single methodology. And we used k-means clustering and clustergram to understand how many clusters we need for each city, which gave us the signatures. Let me start with Barcelona, because it's probably the most well-known case out of these. On the left side, you can see how spatial signatures actually look like in the end. That is the geometry of spatial signatures based on the solution of enclosed tessellation cells classified within the same cluster. On the right side, you can see exactly the same data, but they are just projected onto building footprints. It sometimes gives us a bit easier picture to read, a bit easier map. And for those of you who have been in Barcelona, who know Barcelona a bit, you can start picking those structural aspects of the city. Typical example area, the red one in the middle, which was sort of an infill between historical development on the southeast, which is the historical core of Barcelona, and historical villages on the other side. You can see how the perfect grid of example is merging into existing urban fabric, and in that yellow sort of fringe area around that. And you can also see that we are able to capture different types of non-built area. Barcelona is limited by a steep slope on its northern side. You can see that the right map sort of stops there, while the left one, which shows the signatures by themselves, they're limited by boundaries in this case, not by buildings necessarily, goes further away. Here we have Houston on the left-hand side, it's functional urban area, and Medellin on the right-hand side. And these two cases are interesting to compare because Houston was by far the largest case study, both by area and the number of tessellation cells. We are talking about 2 million enclosed tessellation cells, for example, 3,000 in Barcelona. But in the number, in fact, Houston gave us the number of types only 9 compared to 9 we have in Medellin, which is comprised from about 300,000 enclosed tessellation cells. So it's not the size of the case study which affects how many types we have, but it's its structure and its history. And especially in the case of Medellin, you can see that the city itself is in the steep valley. And you can see the sort of transition of different types of natural environment as we go further away from the city, even though there is no information on topography whatsoever in the dataset. And final two examples are Singapore, the sort of island state, city-state, and Dar es Salaam in Tanzania. Singapore is interesting because when I first look into that, I wasn't sure whether we are actually capturing meaningful signatures. But then when I compared what we see Singapore, we can actually read the different phases of development of the city on the spatial signatures. And in case of Dar es Salaam, probably the most interesting aspect of that is the difference between different levels of informality of the development of the city. So for example, the large yellow area is the most formalized area of Dar es Salaam. And then we have some patches of areas which are less and more formal, informal, and also change in density and such. And because my time is getting over, a few points to take away. Urban form and function matter. Both of them matter, not only form and not only function, but both of them matter, and both of them should be considered together. Spatial signatures, which are only the first phase of the project we will be working for another year and a half on, is a classification of predominantly urban environment, which can gives us information in detail and at scale, and which is also consistent. And if we are able to get a good measurement of our cities, we can understand them better. And that's all for me. Thank you.
All right, let me just change my screen a little bit so I can see everyone. We have plenty of questions and we have about 15 minutes
That's
left.
great.
Martin, just so you know, as we're pacing ourselves, that I'm seeing, I think, 6 or 7 substantive questions and then a few other comments as well. The first question comes from Yuan Liao, who asks, clustering based on so many characteristics, how do you consider the namings of these resulting signatures to make sense out of them?
Yeah, that's tricky. That's a really good question because it's really tricky to do. In this set of 5 illustrations, we sort of decided not to make portraits, not to give names to them. So we say, okay, we have 0 till 18, and we didn't get further to that. But for another case study, which is focusing on the Great Britain, we are doing that, and we are trying to understand what are the extreme characters for each category. So which of them mostly affects the creation of that class. But it's tricky. It's really tricky. It takes a lot of time to actually get a sense of what we are looking at, and it requires a bit of interpretation into what we are looking at. It sort of, you certainly need to be a bit poet to get the description and step back from the purely data-driven analysis in this case.
Great. The next question comes from Alessandro Venerandi, who asks, by considering city areas a combination of urban form and socioeconomics, isn't there a risk of rendering city areas static? I explain myself better. The same urban form can host different sections of population in time. If you tie a specific urban form to a specific section of the population, how can changes in urban form and or socioeconomics take place in time?
What we are doing at this situation is we take a snapshot of a city at one specific point in time. And because we are including both form and function, we are able to make the same snapshot in 2 years. Well, the form will be essentially the same. It won't change much, but the socioeconomic profiles can change. And that gives us it gives us a bit more flexibility in this. So it's actually vice versa. It's not rendering the city static, but more flexible in the change in time. Okay. Especially compared to purely form-based classification.
Yeah. Yeah. I mean, if we have time at the end, any questions I have are all purely demographic, but I think we've got lots of other questions to get through first. David Better asks, it sounds like tessellation can be a computationally expensive initial step. From the final results, classified areas tend to be much larger than the tessellation cells. How critical is the size of these cells and the criteria used to divide them? Is a small but regular grid of cells valid?
We spent a lot of time optimizing the algorithm. So yes, it can be computationally expensive, but to be honest, it's not the bottleneck at the moment. So we've been able to generate a selection for large areas without much struggle at the moment. But this is the question we get a lot. Why do we need to use enclosed tessellation? Can we use something else? Can we use a grid? We haven't tried it, but I know that Chris Joachim in Southampton, they did try to classify urban form based on the grid, and very similar approach if you look only on form, and it worked in their case. But we would like to think about tessellation as more flexible unit than a grid. Then in some cases, let's say we use 100 meters grid, that can be too much for certain differences. If you can recall that image of Barcelona, there was a very narrow strip of yellow between historical core and between example. That's where the historical city wall used to be. That's what is called sort of fringe area in urban morphology, and that most likely would be filtered out if you used grid of a certain resolution. And if you go to, let's say, hexagon grid of 25 meters, it may work, but how do you link classification of building shape to that? You're trying to do a lot of steps which are not entirely necessary, I think, but it may work, and we've seen that it works as well.
Great. Well, our next question is actually from Chris Joachim, who has this to say: as you scale these analyses to national scale, how does the tessellation approach perform in less densely settled areas? Are tessellation cells and plots suitable to characterize rural areas, small villages, etc.?
Well, in terms of performance, it's much easier to generate tessellation in rural areas than in urban areas, because most often in rural areas and in countryside, you don't have buildings. And if you have buildings, you have very few of them. And generating enclosures, it's super simple, easy task. Generating enclosed tessellation within them with few buildings within a large area, it's performant, very performant. How they perform in terms of conceptualization, we believe that it still works because you perceive a space between a certain set of boundaries. And if those boundaries in countryside are further away from each other, our unit should be larger than that. So that's the logic behind that. And whether tessellation cells and plots are suitable to characterize rural areas, we hope so. We hope so.
I guess you're going to find out.
Yeah, you're going to find out soon.
Santiago Correa would like to know, is the data for the historical evolution of cities publicly available? And if so, where can we find it?
Will be soon. The paper is currently under review, and we will release the whole data set, including the whole computational workflow, because it was meant also to be illustration of what you can do with Python open data automatically. So it will be available, and you will be able to pin your own points and expand the analysis with your own places, hopefully soon.
Fantastic. Okay, the next question, I should have practiced this name, I think, in my head a little bit. Yanis, but Paraskevopoulos asks, for classifying function, what land use data were used, and what was the unit of analysis, e.g. block level? Have you used or considered using points of interest or other relevant data from OpenStreetMap for classifying function?
Land use data depended on the case study. So we had land use from open data portals for Barcelona. We've been using national land cover database, or I'm not entirely sure how it's called, for US. And we've been using global land cover for places like Dar es Salaam. And yes, we've been using points of interest, and we've been measuring mostly the accessibility to points of interest on the street network. We haven't been using many of them from OpenStreetMap because we're not entirely sure how reliable those are, but we try to get official data whenever we could.
Great. Umbretta Romice asks, Martin, what would you say is the difference between the spatial signatures and the clustering of form only?
You get a richer picture, as I said. It is a fact that form in this classification has a major role. It significantly affects the outcome, but it can give us a bit more information because form is known, or certain types of form are known to host different groups of people depending on their position in the city and depending on historical development and other aspects. And with spatial signature, we should be able to capture this distinction, whether the same form is inhabited by, whether the same form is within deprived areas or less deprived areas, let's say. That's the theoretical assumption behind the difference.
Okay, I just want to make sure that you may not have a chance to look in your chat and look at the questions, but there are a number of people thanking you for an excellent presentation and the lovely slides. And one attendee asked what you were using for your slides, which Henrique has attempted to answer, but I thought I'd let you answer live because we won't save the Q&A.
Yeah, it's Reveal.js. Henrique responds correctly.
Yeah. And you saw that anonymous attendee said, brilliant presentation. And I'm seeing similar comments in the chat also. Prav has a question, and then I know Levi also has a question for you. But Prav asks how we account for terrain, which I suppose would be something like topography, seasonal weather, historical data versus real-time data. I think they're asking just about how we account for lots of other factors that maybe aren't appearing yet in your approach.
We haven't included terrain data, even though we found spatial signatures which are significantly affected by terrain in the end. We haven't included weather at all. And regarding historical data, we've been using some information on listed buildings, especially in Barcelona and listed areas, to understand whether that area has of historical significance or not, as one of the functional aspects.
Super. Levi.
Cool. Yeah. Hey, so there was one question in the chat that we might want to get to from Sergio Porta as well.
Okay.
Who asks, am I right in assuming that the function metrics inform the definition of signatures as much as the urban form ones? Are they just mixed up together?
We don't make a distinction between what comes from form and what comes from function when we do the cluster analysis. So they are sort of equal. We don't say that form is equal to function, like the form bucket is equal to function bucket. We say that every single form character is equal to every single functional character. So
Sure.
there may be situations where we have more of them on form and situations where we have more of them on function, but it tends to be pretty much balanced.
Sure. Okay. And then I guess the question that I have is kind of related to something you mentioned earlier about the sort of structural relationship between the signatures that you identify and then who inhabits those signatures, right? So I think Rachel also has some questions about sort of demography and social structure in cities. And I guess I wonder, does a deprived person in Dar es Salaam look like a deprived person in Singapore based on their socioeconomic characteristics? How can an algorithm that classifies the city in both places understand that relative relationship in deprivation rather than absolute?
We haven't looked into any of that. It would probably require detailed look into every single class and to try to understand, okay, these are reflecting deprived areas in Singapore and these are reflecting deprived area in Dar es Salaam, then compare them. I don't think I can answer this question at the moment because we haven't even discussed this, to be honest.
So it's been way more on the construction of signatures than the sort of deployment. I see.
Yeah. So far we've been spending most of the time to actually make it work, and we hope that within a few months, once we have the classification of Great Britain, we will be able to look more into what actually it means and what are the implications of different classes to different places.
Sure. That's understandable. I do think that at that juncture, then you may want to look at things like literature on relative deprivation, or indeed how, you know, the difference is experienced between people through their activity spaces rather than necessarily that they are or are not part of a social bucket, which is sort of has historically been a restrictive frame of analysis. But yeah, that was, I guess, the methodology of which you presented is absolutely fascinating and looks super cool. So that's awesome. But I do think that my own interests lie much more in the, once the signature has been developed, once we have these analyses, what can you do with them? And then the other question that I did have waiting in the wings was, again, one that Alessandro had already checked on change, right? So a lot of things about morphological study, you know, what happens when you change the underlying structure or the underlying, you know, components of tessellation? Is it really just a swap of a single node, or, you know, is it much more fundamental than that? So I was curious about your answer there, but you already covered that. So I'm good to go on that one. So change, I think, is very difficult as well with all these like OpenStreetMap stuff and satellite imagery now.
If I may touch on change, I mentioned several times that this is the first step of the project. The second one is to develop an AI model which would be able to pick these signatures based on satellite imagery. And at that point, we hope to be able to update the signature classification every, let's say, year when we have the cloud-free mosaic.
Super. Okay, we've gone to precisely 5 o'clock according to my laptop. And I want to thank you, Martin, for a fantastic and a beautiful set of slides. One of my takeaways was just that your visuals were excellent and a good talk and a really exciting project. But I also want to thank the audience for all of the questions. I love it when we have lots to discuss after the talks. So I really appreciate everyone taking the time to be here today. And I'm drawing a blank, Levi, if we have someone next Tuesday.
We don't. So we have a break because of the Easter holiday and then American Association of Geographers meeting the week after that. So we have a very special thing that will be happening in the next sequence of the SAD seminars. If you want to introduce it, Rachel, that's fine with me.
No, how about we just tell people to stay tuned?
Sure. So
something exciting coming in 2 weeks.
Indeed. So please stay tuned. We have a new phase of the seminars that will be starting very soon. But the first one will be at 4 p.m. on April 13th, 4 p.m. London time. I know that there was some confusion today about the daylight savings time. So please stay tuned to SAD 2020, either on Twitter or through our Eventbrite emails, so that you can find out the next new exciting phase of this seminar series. Thanks a lot, and we hope to see you soon.
Thanks, everyone. Have a great afternoon.
Thank you,
and
Martin.
evening.
Yes.
Yes, thank you, Martin. Everyone get
Thank you.
outside, enjoy that
Yes.
sun if you're in the UK.
Indeed.
Bye, everyone.